Class. Does anybody have any questions about the homework for today? Yep.
Well, it wasn't, like, this is the other homework.
Yeah, the vectors one?
No, for particle.
Oh, okay.
Free body diagrams, and it's not 1 or 4, like the ones that are due today.
The ones that were due today were...
It's not the ones that are due today.
What isn't?
The question that I have.
Okay, that's fine.
Okay. I just wanted to clarify.
Okay.
But, so I was looking at number 3, the solution.
Yeah.
And I saw that you had, like, the normal force of 7 acting on the free body diagram for 7. And I was just wondering, when do you add in normal force?
So this is for the number 3 on the... What is this? Which one is this?
Particle, free body diagrams, number 3.
Oh, okay. So I'm going to talk about that stuff a little bit today, first thing. But, okay, so here's the idea with particle free body diagrams. Number 3. So there's an incline. There's a cart like that, and those... anything with little wheels like that, that's supposed to indicate that there's no friction, unless it says specifically that those are actually wheels that have friction. And so we have a 300 Newton force here, a 20 kilogram block, and a 7 kilogram cart. And this is the ramp. And all you have to do is a free body diagram, so you don't need any angles or anything. You would need to know the angles to calculate it. So a free body diagram of the 7 kilogram. You have the weight. You have a frictionless contact, and I haven't really talked about this explicitly yet, but that's the first thing I'm going to do today. So I'll call that the normal force on the 7. And then we have a pushing contact on the 7 by the 20. We know it's acting this direction. Again, we haven't really explicitly talked about that yet, but I'm going to. But I'll just call that R. That's the contact force between them. So that one, you're asking about the 20, I think. Isn't that right? Or are you curious about this one?
I was just confused about when you're supposed to add the normal force in and when you aren't.
Okay. So let me finish the 20, and then that'll sort of lead into what we're talking about next. So free body diagram of the 20. So on this one, Newton's third law says that since we know the direction of this contact force, Newton's third law says when we go to the other body that's part of that contact, we just change the direction of the arrow and keep the variable the same. Okay? And then there's friction between the 20 kilogram and the ground, and so we treat that as a fully unknown force vector. So I'll just write that as like F or something. Or if you want to use the subscript notation, that's a good idea. Force on the 20 by the ground. And then you have the 300. And so this one has a normal force because that's a frictionless contact. This one, I didn't draw it as a normal force, but this unknown force vector could be broken up like you did it in Physics 1, where you always break it up into a normal force and then a friction component. That just doesn't help us really in this class. That doesn't make it easier to solve any of the kinds of things we're trying to solve. So instead of breaking it up into a normal and a coefficient times a normal or whatever, what you're used to, a normal and a friction force, we just call it all a force vector. But this, of course, is the same thing. I don't know about of course. That seems a little unnecessarily demeaning or something. But this is equal to, I mean, you could break this up however you want into different components. You could break it up into a component that way and a component that way. And then you could call those components whatever you want. So you could call this one N20 and this one friction force. You know what I mean? But that's no different than this. You know what I mean?
Quick question.
Yeah.
Is there a reason why for the free body diagram of the 7 you have only, if we were to have this in an exam and we had 2 contact forces on the wheels, would that be acceptable?
Oh, well, so the thing here is, if this was a rigid body problem, it would be important to have a reaction force at each wheel. Since this is a particle problem, if you think about, so the contact on the 7 from the incline is broken up into 2 different contact forces, okay? And the only thing that breaking them up into 2 different contact forces does is control the rotation of this object. Can you visualize that kind of? It doesn't, it has, whether we break this N7 up into 2 forces or just treat it as a single N7, the only difference is how those are going to affect the orientation of this object. And so since we're doing particle problems here, we don't care about orientation, so we might as well just do 1 force. But once we go to rigid bodies, you would want to do that as 2. Any other questions about this? So maybe let's just talk about these contact forces, and then we'll go back and do a couple of example problems that'll get at this, and then we'll go back to some Newton's third law example problems too.
For the 20 bucks?
Yeah.
Should you have the downward force of 20?
Yes, you're right, I should. Just get that in here. Yep.
Are we supposed to multiply that by the acceleration of gravity to get newtons?
That's what the G, so this G isn't grams, it's, that's what it means, 9.81 or 9.80.
Oh, for gravity. Okay.
Right, yep. So yes, this would be 68 something, and this would be 196 something. All right, so now there are a few types of contact forces we need to talk about, and you can think of this as a first look at joints. Joints are going to be a big thing in this class, figuring out how to treat the connections between bodies. So a joint is a connection between bodies. And you can have all sorts of joints, like, for example, if you have like a pin joint here, a hinge type thing, this can rotate around. That applies certain kind of loads. You could also have like a fixed joint. You could imagine this beam welded to the wall. That applies a different kind of loads to this beam than this pin joint does. You could have an object with a pin through it that can slide in a slot, and that applies a different kind of loads than those other two. But the ones that we care about for now are connections to cables, frictionless contacts between bodies, and friction contact between bodies. Cables, you can think of this as, you can use this general application for anything that's pulling on another object. So you can think of this as pulling. And frictionless contact, you can think of as general pushing. Okay, so cables. A cable applies a force to a connected body first parallel to the cable, and second away from the chosen body. The magnitude of the force is constant along the cable. There's some caveats to that. For weightless cables, that pass over, so if they pass over anything, what they pass over has to be massless, frictionless pulleys. That seems like a lot to ask. Any one of those is a lot to ask. You know, that never actually happens. But those are good approximations in a lot of important problems, because the forces that are due to the weights of the cables and the inertia of the pulleys and the mass of the pulleys is often going to be totally overwhelmed by the other forces involved. And so you can get good results by making these approximations. Okay, so here's an example. So let's say that we have two masses. Let's say this one's 1 kilogram, this one's 2 kilograms. And they're connected each to a cable that goes over this pulley. Free body diagrams of the two bodies look like this. The first one has a weight of 1 times g, and then an upward force of T. And how did I know that force was upward? Because the direction of that force has to be parallel to the cable, so either up or down, and it has to be away from the chosen body, so that means it has to be up. And I mentioned this yesterday. I think for some people it's helpful to imagine including just a tiny little stump of the cable in with your free body, and then that force always just pops out of the stump. And then the free body diagram of body 2. There's a weight of 2g. the rules of the direction of a cable force say it has to be up, and the fact that this cable only passes over these ideal pulleys means that it also has to be T. Okay, so those rules there are enough to let you always figure out how to represent cable forces. Yep.
So basically, you're saying that if the cable, you follow the cable and it's uniformly goes from one body to another, the breakage, you have to use just T. You can't just say T1 and T2.
Right.
And if they break up into different things, you say T1.
What do you mean break up?
Like, let's say if you have a body,
Yeah.
there's supported with two cables.
Two cables. Yeah.
So then you have T1.
Then you do have T1 and T2. But if it's a single cable and the path does nothing but either go through the air or go over cables, these ideal cables, then treat it as a single force variable. Okay. Okay, the next type is frictionless contact. And this is what you use for any things that are pushing against each other. So for frictionless contact, if two objects push against each other without friction, the contact force is perpendicular to the surface of contact. And second, the contact force is toward the chosen body, away from the contacting body. Okay, so that's the difference between pushing and pulling. If you have something pulling on the chosen object, the force is going to be away from the chosen body. If you have something pushing on the chosen body, the force is going to be towards it. Okay? Towards versus away. And then you use Newton's third law to represent the force on the contacting body, like once you go to free body diagram of the contacting body. Okay, so here's an example. So we have this incline, and we have two carts making frictionless contact with the incline, and they're also touching each other. And let's say we have a force of 100 newtons. Let's say this is 5 kilograms and this is 3 kilograms. So a free body diagram of the 5 kilogram cart. We have the weight. And now we're going around the boundary looking for contact. the contact between the wheels and the ground, that's a frictionless contact. So it's no different than any other time that objects are pushing against each other. The ground's just pushing against the cart. And so we know that this contact force is perpendicular to the surface of contact. And we know it's toward the chosen body, away from the contacting body. The contacting body is the incline, so it has to be this way. And you can call that whatever you want. We're used to calling that the normal force, but that's just a scalar force variable telling you how big that contact force is. And the same thing over here. 5 is being pushed on by 3. So that contact force is perpendicular to the surface of contact toward the chosen body. So I'll call that R. And that 300 doesn't act on the 5, so we're done. We've gone all the way around the boundary, and these are the only 2 places that there's contact. And then free body diagram of the 3 kilogram. We have the weight. Going back to this 5, let's call this N5 just so we can differentiate because they each have different normal forces. So now going around the boundary of the 3 kilogram cart, there's a pushing force from the incline that's perpendicular to the surface of contact toward the chosen body, and I'll call that N3. And then we get over here, there's the 100 Newton force. And then we get to the other side. That's the contact between the 5 and the 3. We've already dealt with that once. So now we use Newton's third law. Switch the direction of the arrow, keep the force variable the same, and that's it. So with all of this stuff, this is kind of a theme that's going to keep coming up through this whole class. Try not to think too much about what's happening. Try to be disciplined about using these rules that are laid out, okay? Because, I mean, it's a good idea after you do it sort of sanity check by thinking, like, does that make sense with what I expect to happen? But these rules are going to get you through in the cases, which we're going to get to, where too many things are going on for you to have any intuition about it, and you just have to understand how to use these rules. So like for these pushing contacts, when I got to those normal forces, it seemed sort of tedious the way I was thinking about it. Like, do we really have to think about like perpendicular to the surface, toward the chosen body, blah, blah, blah. That's going to be a better way to think about it as we go on. Okay. What you really want to I think your goal is to limit the amount of thinking you have to do in this class as much as possible. You want to just get to the point where it's just rules, rules, rules. Like, you want this topic to be totally as boring as possible, you know? Like, the only satisfaction from this class should come from the feeling of, like, I'm becoming a very efficient computer or, you know, whatever, automaton. It's not like thinking, like in physics, you have to do all this, like, thinking about, like, whoa, it's a particle and a wave? That's crazy. There's nothing like that here, you know?
Try not to think about that.
Yeah, right. Well, you're in the right place then. Okay, and then the last one is friction contact. Friction contact are used to breaking up the contact force into a normal force and a friction force. We're not even going to bother with that because it doesn't end up helping us in this class most of the time. So in this case, the contact force is just an unknown force vector. And that's all you have to do with that. So let's think of an example like this. So you have a force of 5 newtons. Let's say this is 1 kilogram, and this is 2 kilograms, and it's on an incline. And let's put another external force on this one of 10 newtons. And draw those two free body diagrams. In physics 1, you would have rotated the coordinate system and broken it up into a normal force and a friction force. But we don't have to do that. It doesn't really help us. So we're not going to rotate the coordinate system in general. There will be one topic later on where we will, but for the most part, up until right at the end of the class, we'll just do this. So there's the 1 kilogram box. There's a weight of 1 times g. And now going around looking for contact, there's a 5 Newton force pushing to the right. And then when we get to the bottom, there's a friction contact. And so we're just going to treat that as an unknown force vector. So we'll draw the directions of the two components, and we'll write force on 1 by 2. And then go to the free body diagram of the 2 kilogram box. We have the weight. We have the force of 10 newtons. At the top, we have the force. This is a friction contact. It's the force on 1 by 2. We can use Newton's third law for that. And so this is equal to negative F12, which is the same as F21. And then when we get to the bottom, there's a force on 2 by the ground. And that's how we're going to represent friction forces. Any questions about that? All right, so here's a question. Why not just leave this as, if I had left this as force on 2 by 1, that would have been perfectly accurate. Why would I bother to change that to negative F12? That's right, because all of these are going to produce systems of equations. We have a fixed number of equations that comes from Newton's laws for every body. And we need one more equation for every new variable we introduce. Introducing F21 would give us 2 new variables. We need 2 more equations. Usually we can't do that. And so the way we deal with it is we represent that in terms of the variables we've already chosen, already given, so that instead of, so what we have here is 1, 2, 3, 4 variables, and we could solve this because we have 4 equations from Newton's laws, 2 for this one and 2 for this one. If we left this as F21, we'd have 2, 4, 6 variables, and we wouldn't be able to solve this. So that's the benefit of Newton's third law. Yep.
So we don't include contact forces because that's just included with the friction?
Yes. So this force F12 is lumping together the normal force and the friction force, just into a single unknown vector. But and it wouldn't be wrong to break it up into a normal force and a friction force. It just takes a little extra work that isn't going to give us any results, so we just write it like this. So the normal force is lumped in there and the friction force is lumped in there. Okay, so let's do an example problem that brings some of these things together. So let's say we have one cart, and that has a mass of 1 kilogram, and it's connected by a cable to another cart that has a mass of 3 kilograms, and a separate cable goes over this pulley and connects to the ground. Okay. And then on top of the 3 kilogram cart is a 2 kilogram box, and there's friction at this contact. So first, we're going to draw free body diagrams of each body. And then second, we're going to use these free body diagrams with Newton's second law to calculate the cable tension and all the contact forces. Okay, so I'll just sort of work from left to right. So first I'll do a free body diagram of the 1 kilogram cart. There's the weight. Over here there's a cable tension. So I'll call that T1. Since there's 2 separate cables, we're going to have a T2 also. At the bottom, what kind of contact is that at the wheels? Yep, that's a frictionless contact. So we just have the normal force, the pushing force. So that's perpendicular to the surface toward the chosen body, and I'll call that N1. And then on the back, there's a cable force. So again, that's away from the chosen body, and I'll call that T2. Anybody have any questions about that one? Free body diagram now of the 3 kilogram. There's the weight. There's cable 2. So what's the force applied by cable 2? What direction does it point? It points away, and what's the magnitude? It's positive because you can think of this as a force where we know the direction. So all we're changing is the arrow direction, and we just call this T2. Okay? So there's two different ways you use, well, actually, don't think of this as Newton's third law. Just think of that as a cable that has the same force all the way along the length, and it's always just in the direction away from the chosen body. Yep.
Because the cable's always pulling away.
Right. That's right. That's right. It's pulling on each cart. Yep. It can't do anything but pull. And then down here, that's a frictionless contact. So perpendicular to the surface, toward the chosen body. I'll call that N3. And then up at the top, there's a friction contact between the 2 and the 3. So I'll call that the force on 3 by 2, and that's an unknown vector. And then free body diagram of the 2 kilogram box. We have the weight. And we have a friction contact. So it's an unknown vector. We could call that F23, but we can keep down the number of variables if we recognize that we've already defined F32, and so this is negative F32. Okay, so how many equations are we going to get from these 3 free body diagrams? 6, yep. 2 components of Newton's second law for each body. And how many variables do we have? Hopefully 6. Otherwise it's a problem. 1, 2, 3, 4, 5, 6. So we should be able to solve this. Okay, so Newton's second law for body 1. You know, things would have come out a little neater if we would have rotated the coordinate system, but I already drew it like my coordinate axes are this way, so let's just fight through it. So what are the angles? Did I give angles? I meant to. So let's call this 30 degrees. All right. So on body 1, we can represent this force as T1 times the cosine and sine of some angle. So what's the angle for this one? It's 150 because this angle is 30. Doesn't look like it, but it is. Because you're going from the positive x-axis to the vector, so it's like 180 minus 30. And so that is negative 0.866. That's the cosine of 150 times T1, and then positive 0.5 T1. Now what's the angle for this N1? I'm making this worse, aren't I? Yeah, that's right. The angle between the y-axis and this vector is 30 degrees. So this angle from the positive x-axis has to be 60. So we have 0.5 N1, 0.866 N1. The weight, that's 0, negative 1g, because it's in the negative y direction. So 0, negative 9.81. what's the angle for this vector? 330 or negative 30, either of those will work. And so that is 0.866 T2, negative 0.5 T2. And this system's in equilibrium, so those are equal to 0. So we have two useful equations. The first one says negative 0.866 T1 plus 0.5 N1 plus 0.866 T2 is equal to 0. And the second one says 0.5 T1 plus 0.866 N1 minus 0.5 T2, and I'm going to put the constants over on the other side. Whoops. This should be positive 9.81. All right, well, there's nothing there we can solve. We have two equations and three unknowns. So we're just going to carry this on to the next step, keep this as part of our system of equations, and move on. Eventually we'll have a system of 6 equations and 6 unknowns. So Newton's second law for body 3. What's the angle for T2? 150, yep. So we have negative 0.866 T2, positive 0.5 T2. What's the angle for N3? 60. So we have 0.5 N3, 0.866 N3. Then the weight, that's the easy one. That's 0, negative 29.43. And then we have F32, and I'll break that up into components. So X and Y components. Okay, so we have useful equations number 3 and 4. We had 1 and 2 before. The third equation says negative 0.866 T2 plus 0.5 N3 plus F32X is equal to 0. And equation 4 says 0.5 T2 plus 0.866 N3 plus F32Y is equal to positive 29.43. And then Newton's second law for the 2 kilogram body. That's just the weight and negative F32. So we have 0, negative 19.62 plus negative F32X, negative F32Y is equal to 0. So our last two equations, equation 5 says negative F32X is equal to 0. And our sixth equation says negative F32y is equal to 19.62. Okay, so you can see that equations 5 and 6 let us solve for F32. Then we could plug that. We could do this as a ugly substitution problem. But we're going to end up in this class with huge systems of equations that you never want to do substitution with. So we're going to use reduced row echelon form to solve this, and your calculators will do it. Bless you. So here's what we want to do. We want to set this up as a big matrix that has 6 rows and 7 columns. Every column is going to represent a variable, and every row is going to represent an equation. Okay, so this is equation 1, equation 2, 3, 4, 5, 6. One, two, three, 4, 5. Okay. And each one of these represents a variable. So what are our variables? We have T1, N1, T2, N3, F32X, F32Y, and then the last column represents the constants, and those have to be on the other side of the, alone on the right side of the equation. So that's why when I went through and wrote down the equations, I moved all the constants by themselves over to the right. Okay, so equation 1. We're just going to fill this matrix in with the coefficients of all of these variables. So equation 1, T1s, we have negative 0.866. T2, we don't have. N1, we have 0.5. T2, we do have two T2, positive 0.866. And we don't have any of these. And then the constant is 0. Equation 2. T1s, we have 0.5. N1s, we have 0.866. T2s, we have negative 0.5. And we don't have anything else. And then the constant is positive 9.81. Any questions on how I'm doing this, how I'm filling this out? Now equation 3, T2s, we have negative 0.866. N3s, we have 0.5. F32X, we have 1. and everything else is 0. Equation 4, T2s, we have 0.5. N3s, we have 0.866. F32Ys, we have 1. Constant, we have 29.43. And everything else is 0. And then the last two, F32Y, we have -1. I skipped an equation. Equation 5. F32X, we have -1. And everything else is 0. And equation 6, F32Y is -1. The constant is 19.62. And everything else is 0. Okay, so on the different calculators, different TI calculators, you enter these differently. On a lot of them, you use the matrix function. On TA89s, you can actually use the simultaneous equation solver, or is that what it's called? Linear equation solver. And just enter these in. So if you have trouble figuring out how to do this in your calculator, come let me know. But once you have this entered in a matrix, you just use the built-in function RREF, and it'll give you these values. The way it'll give you these values is a diagonal matrix with all zeros except ones on the diagonal. And then there's one column left over, and the last column that doesn't have zeros and ones gives you the answers in the order that you have them entered. So the first value it gives you will be the value for T1, then N1, T2. So does anyone have these?
29.43.
T1 is 29.43?
Yeah.
Okay. N1?
8.4930. Or 6.
49 what?
6.
Okay. T2?
T2 is 24.53.
Okay.
And please 42.48.
Sorry, 42.48?
Yep.
Okay.
FB2X is 0.
Okay.
And FB2Y is negative 19.62.
F32. Right. Okay. Any questions about that? There are ways to do this problem that doesn't require as big a system of equations. You could isolate a few of the objects together, and there are ways to do it, but I really don't think it's worth worrying about. You're going to need to get used to solving systems of equations this way anyways. I don't think speed shouldn't be like a big concern. I think the bigger concern is just making sure you do the steps right and understand the way it works, Any questions? Okay, let's take a 10-minute break. Come back I'll start at 2:08.
Should we set a timer?
And 15 seconds.